Hello everybody! In this and the following videos, I will introduce and explain the idea of difference equations. Well, in class we already have studied differential equations in the Solow-Croce model. And let me first explain what is the difference of a difference equation to a differential equation. And then in the following I will have a couple of videos in order to explain the specifics of difference equations and how can we solve difference equations. Because in praxis, when we work with data, we basically always face difference equations and not differential equations. Only in theory, when we have continuous functions, we have differential equations. Well, the first differential equation that popped up in our class, as you remember, is the population-Croce model. And it was basically defined in the case where we have the derivative of a function, let's call it here in general f prime of x, divided by the function f of x, was equal to some constant, let's call it phi. And then we can rewrite this, as you know, this is f prime of f is equal to phi f of x. And that is what we labeled a first order differential equation, because we have the first derivative and at the same time on the right hand side we have the function dependent on x. Or in the population-Croce model it's a population function dependent over time. So now, in order to show the relationship to a difference equation, of course, we just operationalize what is the derivative. And you probably remember the derivative is defined as the function at x plus some delta x minus f of x over delta x is equal phi f from x. So the left-hand side is just the definition of the first derivative, and usually we assume that the limit of this delta x goes to 0, and then it approaches the first derivative f prime of x. But let me now rewrite and rearrange, so I bring the delta x on this side and also the f of x on this side, and I factor out the f of x. Then I have the delta, I have the phi, I have the delta x, the f of x is factored out, and then on this side I have just f of x delta x. So this delta x, is, for instance, an interval. Suppose the length is 1. Then you see phi is a constant, the delta x is a constant, so this is a new constant. So let me just define and relabel this as phi tilde. And phi tilde is now f of x, and here we have f of delta x. And now suppose the x here is simply x of t, and the delta x is, suppose, the difference between x of t minus x of t plus 1 minus x of t. Well, if I use this here in this equation, then I obtain here, of course, then I have x of t plus this, and that cancels with this, so I have here f of xt plus 1. Then we have my phi tilde and my f of x, which is x of t. So what we have here actually is what we call a difference equation, a first order difference equation. And what we started with was a first order differential equation. And the difference, of course, is that here we have the differential on the right hand side, the derivative. And in the difference equation we have the discrete form of a differential equation. So this requires that the function is continuous. Here it is discrete. So in general, we can relabel, of course, this box here at the bottom and say the first order difference equation, in short DE, can be written as, suppose there is an xt plus and phi xt minus 1, or in general plus some constant c. Or of course we can say this is xt plus 1. So if we shift if we shift this equation, yeah, t plus 1, one period into the future, if we shift the first equation one period into the future, then this xt gets into an xt plus 1, and that would be an f of xt plus c. Suppose c and phi is independent of time and there are constants in simple numbers. So you see, in principle, equation 2 features exactly what we have here in this box derived, and that is related to the differential equation. So in general, you can say this is what we call a first order difference equation. On the right hand side, you see what we call a first order differential equations. We have already talked in class about solutions of differential equations, in particular the solo differential equations, also the population growth model. Here I will give you some more ideas in this video and in the following about difference equations. Why is this important? Well, it's important, as I already mentioned, in praxis, when we have data points about the previous period, t minus 1, and that is dependent on the today's period, xt. Yeah, it's a time series. And in order to model the time series, we, of course, when we have explicit data, we can just do it with difference equations. For differential equations, I need a smooth, continuous function that features all the data. Well, how can we get it? First, we have to maybe estimate it or approximate it and so on. But this is usually what we not do. We immediately work with difference equations, and therefore it's very important also to understand the basics of difference equations. Well, before I can discuss the solution in one of the next videos, I will start this video with two preliminary discussions. First of all, we have to talk about the idea of infinite and so-called finite series, because this is a tool we need actually in order to solve difference equations in a moment. And the second topic in this video is the idea of lag, the so-called lag operator. That is also a tool we need when we talk about difference equation. It's not needed when we talk about differential equations. There are two topics specific to difference equations. And in this video, I will going to talk about these two parts. And in the next video, I will then come to the solution idea of difference equations. Okay, so let me start about the first point, as I already mentioned. It's about infinite and finite series. Because when we have difference equations, for sure we will have series. So the first proposition I will give here, what we need here is, suppose we have a series, which is 1 plus beta squared, beta cubed, plus beta to the power of 4, plus to infinity. Yeah? In other words, we can rewrite it by saying, okay, there is from t0, beta to the t to infinity. Of course, if beta is 0, then it's 1. If beta is 1, then it's beta squared, and so on. So that's the sum of this time series. And the question is, what is this? What is this time series? Does it approximate to a certain term, to a certain number? Yeah? And that is what we have to find out. And actually, if the beta is less than 1 and greater than 0, then this sum from t to infinity is equal to 1 over 1 minus beta. Okay, so how can you see this? Let's make a quick proof of this. It's quite easy. Well, so this is my first series, so let's copy it again. So that's the series we have to infinity. and that can be written as limit n to infinity. It's a sum from t to 0, beta t to n, and n goes to infinity. And now, well, that's my series, let's call it 1. And now let's multiply the series with beta. Yeah, on both sides with beta. Well, then I have here, not 1, I have beta. But I write it below this. And then I have a beta square, of course. And so on. Yeah? Beta cube plus and so on. So then we have here on the right-hand side from n to infinity of the sum t0 to n. But what do I have here then on the right-hand side? Well, I have beta to the power of t times beta. Or you can say beta t plus the 1. But let me write it like this. Yeah? So that's just my series 2. And now let's subtract 1 from 2. So we have 1, and there is no 1 here. This beta minus this beta cancels. The beta square cancels and so on. But then we have, at some point, here we have a beta to the n. Yeah? But here we have 1 beta more because we have multiplied with beta. So we obtain a term. So we obtain some, yeah, let's say some limit n to infinity. That's wrong here. Let's erase this. N to infinity. We have some n plus 1 because this runs to n, right? And this basically runs to n plus 1 because we have here 1 more. So we have here 1 n plus 1. And if we subtract this from this, look, what we can do, we can factor out this sum. So we would have a 1 plus a beta. So we can factor out, 1 minus beta, of course. Now we have a 1 minus beta because 1, this term above is subtracted from this. And then we have just factored out this n to infinity, the sum term beta t, for t0 to n. That's a common term that pops up here. And this is the first one minus the second one. Okay. But given that I have beta is less than 1 and I have 1 to a very large number, look, n is to infinity, of course this term is 0. Then we have on the left hand side just 1. So I have here 1. I can bring this term on the other side. It's 1 over 1 minus beta. And what do I have then on this side? I have the limit from n to infinity over the sum from t0 to n beta t. And look, this is exactly what we have here because we have here the sum for n to infinity. That's the left hand side here. And on the right hand side I said, okay, that is equal to this, and that is what I obtained here. So it's 1 over beta. So this proposition is true, and I just want to keep this in mind, that if you have a sum of 1 plus beta, beta square, and so on, it's basically if beta is less than 1, bigger than 0, but less than 1, it's 1 over 1 minus beta. Okay, that's the first important point. The second one, when we talk about infinite series, is a finite series. You know, this is infinite, right? Because here we make the sum up to infinity. But what happens? So what happens if we have the following? So we have the sum from t0 to n of beta t. And now n is not going to infinity. It's some number. Yeah? Well, this would be a finite, right? This would be finite. That would be finite. But what is this sum? Can we also find a term for this sum? Yes, we can. Given, of course, my beta is again between less than 1 but greater than 0, I can also find a term for this. So if I make a proposition, let's call it 2, so the finite sum for t0 beta to n, what is this? Yeah, what is this? And actually we can show if beta is less than 0, this is 1 minus beta n plus 1 over 1 minus beta if the beta is in this range. Okay, so how can we see this? How can we see this? Well, first of all, we can rewrite this finite sum in infinite sums. So for instance, we have here the sum from t to infinity beta t. Well, if we make this sum, of course, we add up too much terms, because here we add up just up to n terms. So, but if we subtract now from t, and now we start from all n plus 1 terms up to infinity of beta t, then of course what remains here are just the first n terms. Yeah, so we can write this finite sum and infinite sum by adding up all the terms to infinity, and then we subtract all the terms higher than n, yeah, from n plus 1 to infinity. That would be the same. And that is actually the same. Okay, if this is the case, then how can we show that proposition 2 is correct? Well, that is again very basic now, because we know the first term of this sum. So let me say, okay, this is what we want to understand. It's a finite sum, but it's an infinite sum, and we know this infinite sum is 1 over 1 minus beta. That is what we know for sure. Okay, now the second term, well, what is the second term? Look, it's minus, and it starts, the first term is here in n plus 1. Yeah, beta n plus 1. So the first term is a minus beta n plus 1 term. And then we have the next term is, maybe we make a bracket here, then the next term is beta n plus 2, and so on and so forth. But this basically can be written as 1 plus beta squared plus blah, 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 blah. Look, this is beta n plus 1 first, then beta n plus 2, beta n plus 3, and these terms are subtracted. Okay, but can we simplify this? Well, the first term is clear. This is the term n plus 1. Well, what is this? Look, what is this here? So it's times. Well, this is again an infinite sum, right? This is an infinite sum, because this is also infinite here. But this infinite sum goes from 1 to infinity, so this is 1 minus beta. And now look, we have the common denominator, which is 1 minus beta. So what we have on the top is 1 minus beta n plus 1. So we see immediately that this proposition is correct. Quod et demonstrandum. What we have to show. So in simple words, for infinite sums, the sum is 1 over 1 minus beta. For finite sums, it's 1 minus beta n plus 1 over 1 minus beta. Okay, so that are the first points you have to keep in mind when we talk about so-called series, finite and infinite series. There is one final part, and then I'm already done with this first topic of series, is, let's call it proposition 3. And I'm wondering if we have the sum, which is here infinite to infinity, but the term is not just beta, it's 1 plus t beta to the t. So what is this? So if we plug in 0, well then it's 0, then we have just beta to the 0, which would be 1. If we plug it 1, we would have here a 2 beta. It would be 3 beta squared plus, and so on and so on. And the question is, what is that? How can we find that? Of course, that is not obvious, but we can find a solution also for that term. So let me, without already showing you what it is, let me derive it or prove it what it is. Well, so we want to know this sum of 1 plus t beta t. And how can we write this? Of course, in principle, it is also 1 plus beta squared plus beta cube plus blah blah blah. But it's 2 beta, so we have a second series that starts with beta squared, beta cube plus da da da. Yeah? But look, we also have then 3 betas, so there is a third series that starts here with beta squared, beta cubed, da 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 da, and so on and so forth. Okay, it's just splitting up what I have written here. I split it up in this form. And the reason why I did this, because from this we see the first row is basically an infinite sum of what we already know. It would be 1 minus 1 over 1 minus beta. And then the second series, let's factor out a beta. But if I factor out a beta term, of course I have 1 plus beta squared, which is also infinite. So this is also 1 minus beta. And of course, here I can also factor out a beta. And a beta square. I factor out a beta square, and then I have 1 plus beta and so on, yeah? And this is an infinite series, which is again 1 over 1 minus beta. Of course, okay, now see, I can factor out all these fractions because they pop up in all the terms, and then I have a term that is the first one, that is my beta term, that is my beta squared term. I would have then a beta q term, blah, 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 up to infinity. But look, what is this? On the beginning, we have in front this 1 over 1 minus beta. But well, in the bracket, again, we have an infinite series. Well, this is, of course, it's 1 over 1 minus beta. So in principle, what I obtained here is the product of this, which is 1 over 1 minus beta squared. So in other words, the solution for this sum here would be 1 over 1 minus beta squared. Quad ad demonstratum. That is the rule. Okay, now you see immediately, so if you have a sum, an infinite sum, you just have to think a little bit about how to rearrange the terms in order to find then these sums as one term and not as a series of numbers. All right, okay, that's enough about what you have to remember when we talk about difference equations and solution of difference equations about finite and infinite series. The second topic I want to tackle in this first video about difference equation is what is a lag operator. And most of it is just definition and theory, not so much calculus, of course, as you see that. When we come to the next video, we will talk about the solution. So again, we have a difference equation. Let's call it in a simple framework. So my phi term is 1, so we have xt is equal to xt minus 1. And there is no constant term, let's say. It's just this equation. That would be a first order difference equation. So now what we can rewrite this by using a so-called lag operator, and that is then x of t is L x of t. So this L is what we call the lag operator. And in principle, the lag operator of this xt is defined that this is lagging my variable by 1 time unit. This is my xt minus 1. So instead of having here on the left-hand side the xt minus 1, I can write it as L of xt, because my lag operator will basically shift the time period 1 period into the past to xt minus 1. And this is a very influential concept when we talk about difference equation in a moment. Of course, this idea can be generalized. So in more general, in general, you can say when we have L to the P of xt, well, you can say this is L of L, yeah, P times of my xt, P times, and you can imagine what it is. Here the L is basically 1, so it's then shifting it to t minus 1. Here it's P, therefore it's shifting my x to t minus P. And this is a general rule, and now you wonder, what is L to the 0? Because here it's L to the 1, shifting it. Well, L to the 0 does not shift anything, so you can say it's 1, or if it's in vector language and matrix language, it's the identity. Yeah, that's the identity. Identity. Yeah, so L to the 1 is the identity operator or identity element. The final thought that sometimes pops up when you talk about difference equation is a so-called lag polynomial. That's my last point I want to illustrate, the so-called lag polynomial. You all know what a polynomial is, right? For instance, x squared plus 2x plus 1. That's a second order polynomial. Or x cubed plus 2x squared plus 1x minus 5. That would be a third order polynomial. Okay, in the lag polynomial, usually we use this symbol phi of L, is basically then the first lag operator, which is for L to the 0, which is the identity element. And then it's written as minus 1 for lag 1, of course, minus phi 2 here for the lag 2, minus phi 3 if you do then the lag 3, so xt minus 3, minus 4 L4, and you can imagine that this goes until order P, shifting x to a lag P. And this guy here, this phi of L is called the lag polynomial, because if you would multiply x, if you would multiply, so if you have f of L times my xt, what would be this? Well, this is just an application. It would be, you multiply the right-hand side with xt, and you see that's just xt. Then you shift the xt minus 1 here, here shift the xt minus 2, minus, and so on, until the xt minus p. And here you can see this is a lag polynomial. It's a polynomial function just for shifting the axis by one period backwards. Okay, so keep these two things in mind. In my next video, I really start discussing and solving difference equations. Have a good day. See you soon.